All right, good day guys, welcome again to another tutorial on structural steel design. And in today's tutorial I'll be showing to you how to go about the block shear in your design of steel connection. Okay, and we have a problem here that we want to solve. It says a 686 by 254 by 125 universal beam is connected to a column by web cleats with a single row of bolts. If the reaction is 350 kilonewton and there are 4 20 mm diameter bolts through the web as in figure below, check if the section is adequate for block shear failure. All right, for shear block failure. Yeah, and like I said earlier, all that we need as touching our steel design is referenced from the code. We have everything in the code of practice. So what does the code of practice say as touching block shear design? Okay, so this is exactly what we want to look into. Clause 6.2.4 of the BS 5950 speaks about block shear. So let's first put that down so that you may be able to make references to it as we proceed. Okay, clause 6.2.4, all right, BS 5950 speaks about that. All right, so what does it say about it? Let's now go back to read what it says. It says that for the block shear, to determine the block shear, we have a formula. PR is the block shear, all right, is determined by or from PR is equal to 0.6 py, which is defined earlier, all right, as the strength. T is defined here as the thickness, bracket LV, which is defined as the length of the shear face, and we are still going to discuss that from this figure, and also plus KE, K subscript E, which is quite different from K. All right, K subscript E here is the effective net area coefficient from 3.4.3. we are still going to get to this also. Okay, we are still going to get to that 3.4.3. so this is it. You can see where we are here now. Okay, so let's just get back to where we're coming from. 6.4.2. okay, 6.4.2. sorry about that. Okay, over there. Did we say 6.4.2? 6.2.4. all right, 6.2.4. okay, so we have been able to speak about KE, that's effective net area. We're going to pick references from this clause, all right, and then the LT, which is the length of the tension phase, we're going to pick reference from figure 22, and then we have K, which exactly is here, all right, and D subscript T, which is the old size for tension phase. Okay, so let's just get to work. So the first thing we're going to do is to bring out our formula that we're going to be using in solving these things. So we have P subscript R is equals to 0.6 py t bracket L subscript V plus K subscript E bracket L subscript T minus K dt. all right, and the thing is this: we have been able to speak to ourselves concerning each terms of this formula. So let's bring out their values one after another. Okay, so the first thing we want to discuss here is the py. what is py. All right, so it is quick, we can be quick to assuming that our py would be anything. Say we want to assume that it is a S275 grade steel, okay, and someone might be quick to assuming that, okay, if we are picking into S275 grade steel, our py is supposed to be 275. Okay, somebody can be quick to doing this, but this would not be totally correct if you are assuming directly like this. What you first need to do is to confirm what about this element. You need to look for the properties of this element, because right from table 9 of our BS 5950, you discover that from table 9 you discover that the design strength is also determined by the thickness T. You see that now? So you need to begin to pay attention to information like that. So let's first look for the part and the information on this. Let's find out what about this section. And now to do that, you need to make reference to the Steel Designer Manual, the one I gave earlier. Let's check the Steel Designer Manual. Let's reference page 1166. Okay, we're almost there. So you're going to look for the universal beam. You know what we are dealing with is a universal beam, so and that's exactly what you would look out for. So we are already at the universal beam now. So you're going to look for this section in particular, 686 by 254 by 125. Okay, so it means this is the section we are talking about here. This is the section we're talking about here. Now the thickness of the flange, which is the thicker section, okay, has a lot to do in the determination of our flange, of our strength rather. So we have 16.2 as the capital T, and that's exactly what we need here. This is a capital T, not a small t, so we pay attention to that. So it's a capital T. All right, so our capital T here is 16 point, what do we have again? 16.2. you can see 16.2. all right, so and the small t is 11.7. 16.2 mm, while the thickness of the web, all right, is 11.7. okay, so this can lead us to determining what py will be. Okay, so py from table 9, let's go and confirm if it will be 275 or otherwise. Okay, so to do that, you look for table 9 of the code of practice. Okay, and that should be somewhere above. So let's patiently look for a table. Okay, well, this table 12, we're almost there. Table 11. Okay, this is table 10. Now table 9 is here. Now this is it. Table 9 speaks of the design strength. If we are assuming a S275 grade, okay, which is to say that assuming, let's assume S275 steel grade, it will mean that py as to that table 9, from table 9, the thickness that we saw right now from the Steel Designer's Manual for that particular steel member we're designing is greater than 16. So it means that we will not be able to use 275. because we can only use 275 as the design strength of this steel grade when we are having a thickness equal to 16 or less than 16. So it means that we'd have to go for the next one, which means that for any thickness equivalent to 40 or less than 40 but greater than 16, we can use 265. 265 is what to be used. All right, so the thickness is above 16 but less than 40, so it is 265. You see why it is not advisable to jump at what your design strength should be. So this is how we came about this. Okay, so we can go for the next one, okay, which is the thickness T. We have obtained that here, 11.7. all right, good. So LV, what is LV? Let's check from what the code calls it. Okay, so from the code of practice, let's see, 6 point plus 6 point. We're looking for clause. Okay, 6.2.4 will pass there. 6.2.4. Now look at it now. So the LV is the length of the tension phase and will be in reference to figure 22. Now look at figure 22. Figure 22. We have different kinds of connection mode here, and whichever applies to our work is the one that we would pay attention to. So if you look at this now, this looks more like what we're dealing with. Looks like what we're dealing with. So this is LV on the vertical and LT on the horizontal. All right. So and it's from the first bolt to the edge or the end of that particular plate. Okay, so that's LV. Now looking at what we have here from our question itself, you will discover that the LV in our own case would now be addition of 75. Oh, this is way too thick. 50, 50, 50. Did you see that now? So from the code, it referenced that it's going to be all in this region that represents LV, and your LT would be this LT. Why this will be your LV. You see that now? So this is exactly what the code speaks about. So that will mean our LV should be taken as 50 plus 50 plus 50 plus 75, and that should be 225 mm. So LT also would be 60 mm, which is way clear. If you have any challenge with that, please do well to make contact with me and I'll answer to you. All right, so that's LT. Now we have the next one, which is K. This is KE. Now looking at the BS5950, what does it say about KE? All right, it says KE is the effective net area from 3.43, but K itself, which is different, is a coefficient with values as follows. For single line of bolts, K is 0.5. Two lines of bolts, K is 2.5. So for our question, our K will be 0.5, seeing that we are dealing with a single line of bolts. But KE will need to reference this. So before we go and reference that, let's put down our K. Our K is 0.5 for single row. All right, so let's reference for KE. So when you go to 3.4.3, you discover that for grade S275, KE is 1.2. So we need not to bother. 1.2 for grade S275. Okay, so what else are we looking for? Our D, and this is the diameter for the standard hole. All right, standard clearance hole, so which we are using a 20 mm bolt, and I showed to us in the previous class that for the standard clearance is going to be plus 2 millimeters. Okay, and this would give us 22 millimeters. Okay, so to put all together for our result, we would have something like PR equals to 0.6 multiplied by 265, okay, multiplied by the small t 11.7, then into bracket LV is 225 plus KE 1.2, LT is 60, and its K is 1.2, and D subscript T is 22. All right, so what we have here should be around 5 to 8 kilonewton. All right, and you see that it is observed that our block shear is greater than the applied load. Therefore, this section is safe. So you see, in a simple way, we've been able to design for block shear. If you have questions around what I've just done, please do well to reach out, and we'll see you in the next module. Bye.